Data coming. Okay, so first things first. As you might remember, during the last lecture we have created this CMyInt class as part of the CVP classes example. Since this is quite a useful example, first thing to do, we will just create a new project and move it into an own project, and then we will create another useful class, a self-made string class, which will allow us to, in a convenient way, interact with strings. And once we have done that, we will take a look on what the final project will be for the homework. So I will present this today, just not at the very beginning, since if there are some people that are coming a bit late, so that they can also see it in real life, in real time. And if we have enough time, we will take a look on the different STL container types and generally how and which functionality the STL library offers us. So as mentioned, first let's just create a new project for our CXInt class. New project, it's just a console project. Next, it's just my int. Let's call it my int. Create, and we will do it slightly more elegantly. So we'll create an own class. You can use the class wizard for that. Basically, there are three ways how you can create a class. You can just create individual files, and then that's it. Or you can use this wizard that will create both files for you. And I think there is also some third method somewhere. Right, and the third way is you can just create the files not from this interface, but really by hand inside whichever folder you want them to live. Where did we create that? Can quickly copy the full path from there so that we know where we put it. Okay, and the third method is that you will just create the files here by, let's say, new text file, then you rename it to CNCPP. And actually, you use this method quite often because this allows me to first, for example, create a folder and put it into a subfolder, so I can manage a structure of a more complicated project much easier. And at this point, oh wait, I didn't start screen sharing, did I? The recording is running, but the screen sharing was not running. Sorry about that. Why did no one say anything? Okay, so we have this, we have this. So I need to repeat a few things. So as mentioned, you can create a new class either by just add and class. This allows you to specify a name and then a name. And then you can edit the file names and also set the base class. The other method is that you just add individual files and rename them, although this usually adds them at the root directory level. So the other option is that you create files directly in your folder, or you create a subfolder for them, and then here you can use the add existing item command to add those files to your project retroactively. Okay, so it created here our myInt class, so let's copy the content from our implementation. Given the simplicity of the project, we don't really need to break it up into multiple files, but since we want to demonstrate proper practices, we will do that. So here we just remove all the implementations of all the functions, except for everything that's one-liner. So I like, especially if these are like alias functions or simple getters and setters, there I like to simply keep the functions inside the header file, as it's more convenient this way. Okay, so we need to add the type so that we have everything. Let's see, that should be fine, that should be fine. We need also a file for the test case. just main CPP. Okay, and then we just copy our test case from here as well. Okay, do we have more test cases? I think not. Yeah, we can rerun it to see if it will still work. Something's not right. Right, this wants to be an int. And right here, the default parameters, of course, we only specify in the header file, and we don't repeat that specification in the CPP file where we implement the actual functionality. Okay, so we run it again to see if everything works fine. Well, it didn't crash, but we wanted to put a breakpoint, which we forgot. So let's run it again, and we see that it seems to work. So as you remember from the last lecture, in C++ you have this notion of operators, like this XOR operator, or like the addition and subtraction operators, which we have not yet implemented. There are, of course, assignment operators and this copy constructor. So if you are assigning variables to each other, or creating new instances of variables from other variables, these are used. Generally, one could probably simplify it that the assignment operator would just use the copy constructor would just use the assignment operator. So we could, for expedience, implement it. So as you see here, these are quite identical. The only difference is that this one is clearing data while this one is not. So what we can do is we can just turn this into a one-liner in the header. So here. But before we can do this, we need to initialize the variables which are expected to be initialized by the other we are missing a include here hash include something that just gives us a definition of null. Since null is, as I already mentioned, I think a couple of times, not a actual C++ keyword, but in reality it is just a preprocessor definition for just 0. So we need some header which includes that. Of course, we could go the modern route and write nullptr, which is in fact a modern C++ keyword. At least it should be. It is not defined anywhere. Although if you click on it, then you can still at least enter some Dingsbums, the framework file. But generally this is just defined as a keyword, so this would work without any includes. But since we might want to do other things here, like memset or something, it is good to have an include, at least the std library, so that we have the very basic features. Oh, and I forgot here the semicolon. Now this still is not really a one-liner, so what we can now also do to improve on that is we should create another constructor, one that does not do anything. And in this case we will specify that one. So if we would have this situation, trying to use this without any arguments, the compiler would not really know whether I should pick this one or this one, since for here we allow both arguments to not be specified. So what we need to do in such a scenario is that we remove the first default argument, such that the compiler knows instantly which constructor to call if we call it without any arguments. And here we will use this to initialize our data. So this way this really is a nice one line, and now we just have to implement this one thingy, and it does not contain much, it sets everything to null. Okay, Another operator which one may encounter quite common is the comparison operator. So equals equals, as you see, it is quite similar to the other one, just that the comparison operator obviously just does a comparison and it returns just true or false. And in fact, such a comparison operator, if you have something where the semantics of are greater or lower than something has a meaning, so even obviously with numbers but also with strings you can usually compare them, and in principle everything that can be represented as a block of memory can have a greater or smaller semantic, which is very useful if using such types as keys for maps or similar. And therefore what one usually would do is one would implement a compare function which takes a argument and it returns const. It returns 0 on match and it returns -1 if the one is larger than the other and 1 in the opposite. So -1 if in one case and -1 in the other case. So here, since we use the equals equals operator, we just return compare from other is 0, and we can implement, of course, the not equals operator. Where's my mouse? The not equals operator just by checking if it's 1 or -1, and then we can, of course, implement the greater equal as well as smaller and smaller equal. Smaller equal just by applying the right operators to the return argument. So as you see, it is a very smart and simple way of implementing a whole bunch of operators just by providing one compare function which is slightly more generic. It is generally a very good practice to try to write your code in a way where you are not repeating over and over and over the same code blocks, because such code with a lot of repetitions is not very maintainable. If you decided that you need to change something about how one of the code blocks works, because you change some underlying properties of whatever data you are working with, you are then forced to update all code blocks at the same time, or rather one after the other. Quite at the same time, of course, is not possible for a human being yet, unless you can clone yourself. So it is just annoying later on to change it. And if you try already while writing your code for the first time to see, as soon as you want to write something that you already have something very similar, then instead of copying it, you just take the thing that you would want to copy, just cut it out, put it into an own function, and then just call that function. Compute-wise, of course, calling a function is slightly slower than having the code in place, but in practice this is absolutely negligible. And while the memory usage, of course, of having duplicated code is not very large, it generally is, all in all, more optimal to reuse code than to duplicate code. So now we will implement our compare function. As you see, the difference between C and C++ is that here all our functions have this namespace of our class such that they can access this keyword together with all the class defined properties. Okay, so for compare, what we can do is first we check if this. You might notice here I didn't use this. Here I chose to use this just to demonstrate how it is used. So it's quite equivalent to just directly so if this is not equals the other count, so just demonstrate that this is quite equivalent, and since we are here referring to the other, it's quite nice to see the symmetry in this. So first we check whether they are not the same. So if count would be the same, then we know the numbers at least use the same amount of memory. So assuming they do, we can here just return memory compare, which it doesn't like, so we need to include it should be in this. Do we need stdio as well? It should be in the lib. We can of course include Windows, but that would be annoying. Wurscht, then let's include just everything. For whatever reason, memcmp. It should have been in the stdlib, but for some reason it didn't found it. So before we run into a compile error, let's just include the Windows H, which includes pretty much anything that one might need. Data, and we just pick one of the variables to take the count from. Since we know they are the same, this will work. And memcmp works exactly in that described way. It returns 0, 1 or -1 depending on how the memory blocks when compared to each other compare. And if you are curious how this comparison actually works, it's extremely trivial. It just compares at every offset the bytes with each other, and then if it finishes the comparison without finding a mismatch, it returns 0, and if it finds a mismatch, then it just returns you which character at the offset where the first difference was found is greater than the other character. So it's quite trivial, but usually you only need to impose a sorting on your data, unless you are displaying it for human consumption. The actual ordering rule is not relevant as long as it's always the same. So such a simple ordering mechanism works fine. But before we finish with the function, we of course need to handle the case where these two are unequals. So we can first check if this is the case, and then we can just return either 1 or -1. We can choose what, and in the other case just return the opposite. And in principle we don't even need to do the other comparison, because we explicitly know since they are not equal. So in principle we could also make the code more elegant like this. The last else is also kind of obsolete, because since here we have returns, we could just write the whole code like this, since every return terminates the control flow. So that's like the most least character way of writing, except of course for this not being necessary, this compare function. You might of course in your own applications experience more complex scenarios where you have data which are not just one piece of memory, but where you for example would have like 2 or 3 independent memory regions that will make up the data for your object, in which case generally you could just make the comparisons for each block one after the other, and then you would also get a reasonably well performing compare function. Okay, so we have this, we have that. We could test whether that works as it should. So we have already our two ints here. So let's say all p1 is equals this is less than this, which should be true, and the other b2 is this is greater equals, which should be false. So let's run. We have a bug somewhere. Our XOR implementation is not performing as it should, although I think the issue is rather with our constructors, because when we run it again we can see that it crashes. Here order, or is I too much? I is 0. Data. Okay, let's see. This works fine. I think a red will not be initialized, but I think about it. Yeah. The reason is that before it by default went into this case and it created some data for us. So now we'll need to add a function resize. Let's say we want count 2. in principle it would of course be also maybe more elegant to create it directly, to make it directly an argument in the constructor, but then it wouldn't know whether we are giving it a value to hold or a new size to create. So what we can, for example, I think for now we will just go with the resize because that's the most straightforward solution. So let's add void resize size t new size, or rather new count, since we are doing this in multiples of 32-bit. So we create our here resize function, because if count is greater or equal new count, then just return, because there is nothing to do. And since we are lazy, we will switch here from the use of new to the use of malloc size of int times count m count. And here we need to use 3. And this allows us now here in resize to use the realloc function. So right, and we of course need to add a casting operation here. Let's just be lazy and copy this. Realloc takes as first argument the old data block. As you might remember, I think we have already taken a look on a realloc when we looked on memory management. I'm sure I mentioned it back then that realloc allows you to reallocate a block of memory in a efficient way. So if it can, it will just increase the size of the existing pointer, and if it cannot, because there is already something in the memory address space at the offset which we would need to assign to this variable, then it will create a new block somewhere else where there is enough address space left, and then copy the data, in which case it will return a different pointer. And it is quite convenient. If I recall correctly, it is specified such that you can specify a null as the first argument, so in which case it always allocates a new block. We will test it in a second, so we'll just see whether it works or whether it crashes. And as you see, it works fine, so it is happy with getting, in some cases, null and then just allocating new data. So let's compare here our so now let's go back to our test case, which we initially wanted to run, and see that, as you see, it works fine. There is one use case which we should also take into account. That would be the case where we want to go to make this comparison. So we would obviously want something which is a number which is longer to be considered greater, although that might mathematically it would not be correct, because the number only having more bits doesn't mean that it is longer. So technically we should here pad the other number with zeros and then compare the value, also using memcmp, because the computers by default, or at least most computers by default, use little endian encoding, would also not give you a mathematically correct result. So I think we should just write a comment here. This function mathematically correct comparisons. Okay, so we have this, and there is one other sort of operator which I think I may have shown you when working with the handle, with the smart handle that we have used in the last lecture, but now let's use it explicitly. It is an operator which allows us to implement automated casting. So if we go back here to our test cases, let's take our, let's say this one, and now let's say we want to assign int64 is equals, well, we need a name for it, i64, is equals my int, and as you see, it does not allow us to do the assignment because it doesn't really know how to do it. So what we can do now is we can implement a um, which then will return. For now I just return 0, but of course we will later want to give the function a body. And now as you see, we can do the assignment. We can also try to assign it just to a normal int, 32. As you see, it also works, and the reason why it works is because the compiler will look whether there is anything that my int can be cast to, which then would, in the second step of an operation, which would then have another casting operator to the type we want. So if we put a breakpoint here and run the code, we will see that we should end up in our 264 operator. And as you see, we do. So this way, ideally, of course, we could implement an own just to int conversion, but depending on what we want to do, such an approach might be good enough. So here now, of course, we want to finish this. So let's say we need to create a variable, return, which is equals data 0. Actually, let's do it differently. We'll first make it equal 0, then we will check if count is greater equals 1, so that we know we have at least one entry. Then we make it equals data from 0. Then we make the same thing again. Okay, that will be a bit more than a single line function. But still, such a casting function, it's usually convenient to have it, to leave it in the header. So if it's 2 or more, in which case we of course need the next offset, and then we want to cast it to int64. And here we want to use an OR operation, and then we want to shift the whole thing in this direction by 32. So basically what we do is we get this 32-bit integer, we make a 64-bit integer from it, then we shift all the bits to the higher position, and then we use OR to apply the bits onto our return variable, which before contained zeros. So now when we run it, we will see that we got our result. And what we also can do here is we can add some high order bytes. So let's say here we add xFF. And now when we run it, we'll of course see that this one still contains 3 because it was casted down. So while we return the 64-bit number, the top portion has been discarded. But if we inspect our 64-bit number, we should switch to hex for a better view. We see that it properly placed the higher order double word where it should be, and the lower order double word contains the result from our XOR operation of 1 and 2. So as you see, with these mechanisms, you can in principle create something that is very flexible and allows you to cast different to convert different types into each other. So we can add another constructor, for example one that takes explicitly a 64-bit number, and since we are lazy, we can just use the other constructor to work with it. So here with the other constructor, the lower order bits we can just pass data to, because it will truncate the higher data. Of course, doing it this way will, depending on our warning settings, but in proper projects you should set your warning settings rather high, so it would complain that potential loss of data, in which case you would want to add here an explicit conversion. And for the next thing, we just shift into the right this time, 32 times our input variable, and this way we can create now a variable from int, And if we would want it, we could, for example, create variables which would start out with start out as float, for example, and then have something that converts the floats to 64 to integers. So in principle, you can make it quite flexible. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. Let's see if this works correctly. Okay, something's not right. Oh, we used 5 already. Then let's call it 6. And here, as you see, again, in this case it just truncated. In this case, it failed. Let's see what's wrong. So clear 0, 1. Oops. Okay, so our conversion here is not performing correctly because our data inside int6 is correct, just that when trying to return it something fails. So let's inspect what is not working. And by the way, let's just take a look on the build log, and as you see, it complains here, as mentioned, that there is a potential loss of data, as well as here where we are assigning it to a shorter data type. But let's look here. So what might be wrong? 1, 0, 1 and 0, 64-bit. Seems to be shifted in the right direction. Let's just see what it does. So our initial value is all zeros, which is okay. Do one assignment. We want to do the other assignment, so we check first this. This is correct. Then we check that. This looks also correct. So let's see what's the result. The result is not correct. Interesting. At some point it must be doing a conversion which we don't want to. I'm just not sure why. I mean, we can write this differently, although that should not change anything. Let's quickly check whether this solves the issue. It would be strange if it would. Yeah. It somehow decides that this, let's just cast this again to 64. Why? This is correct. Oh, no, this one is prefilled with the wrong value. Why is that? Is that here? I was not careful enough. Apparently we have the problem already further up, but this doesn't explain why it... I assume what it is doing is that the value which we have here in our 32-bit integer is considered to be signed, and when doing this conversion it wants to maintain the sign, so it fills up everything above it with ones, so that we still get a negative number. But this is not what we want. We just want to assign this without such trickery. So what we can do here, we could either use memcopy, or we could just cast this to unsigned. That should already fix the issue. Let's quickly inspect. Yep. And just for good measure, here we can do the same thing, just to ensure that we will not run into the problem in any other scenario. So now when we inspect our variable, as you see, it contains the right data. So to summarize, we have operators which allow us to convert any type into whatever other type we want within reason. We could also have a function which would convert this to a string, and then place the numerical representation, the textual representation of the string into it. We could convert this to smaller types like short or char, of course probably losing data in the process. How we handle such a situation where there would be a data loss is of course something we would need to think about, because the compiler here would not warn us, so we could either just ignore it, which with some types of errors is a viable solution, or we could make it throw an exception whenever the system detects that we would lose data. So depending on where and for what application you would want to use such an object which allows you for such operations, there you would need to ensure that the behavior in case of error overflow is compatible with your security requirements. The most elegant approach is to just throw an exception, or you could also have a special function to convert. So instead of having like this operator, you would have a function which gives you this type. We can demonstrate that maybe. So you would have your to int64 ball okay is equals null. And the asterisk. So so first of all, we always return a value, but here if count is greater 2, then actually two things. First of all, if this was specified, because this could be null, and then let's say we just dereference this. We don't need the second if. We can use the trinary operator. False, true. So here now we have a function which will cast for us, so it's also quite easy to use. Instead of this, we just write to int64. But then we have the opportunity ball okay, to evaluate the result, the content of B, and then we know whether it was successful or not. Of course, this could not be just a boolean value. It could be a value that generally specifies an error out of the whole list of errors, so for example an enum. And at the same time, if it's not specified, since we added a default argument which is null, and here we check whether it is null, so in this case it would ignore the potential error. So in this case here we just have a one-liner where we just return whatever the function returns. So this is the downside of using operators, that you only have one return value. Usually you cannot communicate an error in other means than by throwing an exception. So for example here we could actually always evaluate the BOK variable and then throw an exception if it's not fine. But that's actually we should do it. First of all, of course, we will move this here to the rest of our functions. As I mentioned, unless it's a simple function, we should not keep it in the header. And now if we want exception, we could create our own exception class, or we could also have it as part of this as int error struct int error enum enum can be error none, everything's fine, overflow, and then we just have one variable, or yeah, which will contain our error code. So here doesn't need to be equal to anything. Turn red, and now we need to do this. So reference on that. If this is false, then throw as int, and we could use the curly brackets to provide an argument for the variable here, or we could actually create a proper constructor for our Alright, and we are missing the namespace, so we need to add the namespace here. Okay. So that's one thing, and what we also could do is we could have a variable for and throw on error, which will throw whenever an error is encountered. So let's say we don't want crash, so let's say it's false, but we could change this later. Let's see, this we need to initialize here as well. The other constructors use this constructor, so it's fine, or this one, so this is already initialized. So then having this variable, we could then check, so if not true and throw an error, then throw, and then to control this we would add a setter function, void set throw an error for the set. We can by default even provide an argument, since the expected case is that it will by default be false. Then we can have a getter which I wouldn't know what in this case you would want to use it for, but generally it is good practice to also have a getter function, so that if you can set some variables you can also get their values, which might come in handy later. Okay, and one last thing we can do, as you see we have here this assignment operator. If we would do a thing like where is it here, let's create another one, my int 7 is equals 1, 2, 3. We will step through it and you will see that it is a bit complicated, at least although it might be smart enough, but I don't think it will be. Let's see. Right, so we entered the constructor and then okay, it was smart enough. I would assume that it would go through creating a copy and then assigning it, but it picked the right constructor instantly. Right, that's why. So let's do it differently. This way we can force the behavior. So we create this without any data, and then we try to assign a normal number to it. And as you see, it allows for the number assignment, and the reason is because it will create an instance. So if it sees an assignment, it looks, okay, is there some object to which I could cast the argument, which then I could assign. And in this case, it sees this here, and then we go through the whole process of creating an object. Then we enter our assignment operator. Let's get it out, and then we need to destroy the object. So as you see, it is kind of wasteful, maybe not that much memory-wise, because the memory gets freed instantly, but computation-wise it is not ideal, since we do an allocation and a deallocation of memory, so that always takes some time. So what we can do to improve such a use case is we can create an assignment operator which will directly take a, let's say, a 64-bit integer. Suck. And then of course we need to implement it somehow. So let's go here. Where would be a place for it? There is that assignment operator. Let's put it here. And we will just copy this. Although we need not to forget to do it. So we can do. We could go with resize tool. This will take care of handling all these special cases, although this will not resize it down. So let's say if it's not equal, then it will return, otherwise it will reallocate to a smaller size. And then of course we here this is already, so that should be fine. So this way our operation here will be, especially if we would pre-allocate with something. So let's say 1, 2. Let's see. Right, we forgot to return ourselves. you remember the assignment operators always return a reference on our object. So we broke something. Probably we broke this thing again. Yeah, mdata 0y. Alright, this should be is equals. If it's only if it's the same, then it doesn't do anything. Then it, in else case, it does. So now, when we enter our function here, we enter the special constructor. So then, where we enter this resize, but the resize doesn't do anything in this case. And then we just do the assignment. So we, by creating more custom assignment operators, we can work around the need to create objects when doing assignments from numbers directly. So this is quite useful and generally a good practice. So we have this, we have this. I think we have everything that's worth mentioning at this level about the ability of assigning things from different types to other types. Oh no, there is one thing I should mention. You might feel it would be convenient to add a constructor which would take a Boolean type or a operator which would cast to a Boolean type. This should be done very carefully because almost anything can be cast to a Boolean type. So, and the Boolean can be more or less assigned to any integer. So you can end up in situations where the compiler would, where you're assigning two different types, one to each other, one to the other, where there is no proper assignment, but the compiler will see, oh, I could make in this case, my int out of it, and then I have a Boolean, and then I can assign that Boolean, and this would not be great because you would lose data and you would not even notice it, so it would not warn you. So one thing that can be done to avoid such issues is you might opt for not providing an operator which casts to Boolean, so like this one, operator bool. You just don't provide it. And the other option is if you want to avoid the constructors which you have here from being invoked implicitly as a part of some casting operation, you can use the explicit keyword which will restrict the invocation of this constructor to really when it is written in the code that it should be invoked. So when you write see my int something, then it works, but it will not automatically try to do the casting for you. So this is something which generally is a good practice to do. Okay, so we have improved a lot on our myInt class. Are there any questions about it? Okay, if there are no questions, then I think this would be a good point. What was it? This complaining here? Maybe, there was a typo. Explicit without e. Okay, so I think this is a good time to present you the final project which you will need to implement until the end of next month, plus 1 week more if you really need the extra time. So let's create a new project for that. Create new project. Console application, and we'll call it C variant. In computing, a variant is a data type which can represent more than one data type. So, for example, it can be a string, it can be a number, or more precisely an integer. It can be an integer of different sizes. It can be a float, it can be a white string. So that would be like the absolute minimum what a variant needs to be able to do. And usually more advanced variants can also contain a whole list of other variants, so that the variant can have the type list or even the type map. What a map is, we will take a look at a bit later. Basically, just to quickly maybe address this, a map is a sort of structure where you have a key and then you have a value which is associated with the key. So like in a array or a vector, you have like 0, 1, 2, 3, 4, 5, the index, and then you have as many elements as your highest index is, -1, since you start at 0, and you can only address by the index. If you would have a map, then you could, for example, first of all, not use an index, but use a string or anything that for which you have a is equals and is less than operator. And I think the equals operator is even optional because you can construct a equals operator from using less than operator. So you just compare both ways, and if both comparisons fail, then you know that neither is bigger than the other one, so they must be equals. So such data structures are quite useful because you can store data for arbitrary keys, and the keys, and you don't need to exhaust the key space. So you could of course also use an integer as key, and then the advantage over a sort of array would be that for every value that you don't have a for every key that you don't have a value yet, you would not be using any memory. So the task at hand, let's write it down. Oops, not too much. Will be to create such a variant structure. So project a C variant class, variant class, which can various data types. 1 int 8, int 16, comma int 64. I forgot int 32. Int 32. Int 64. Also unsigned. Then it would be good if it can contain also float 64, aka double. Optionally float. Okay. Then third thing, a string array of chars as well as a vchar of chars and vchar. So it should be able to differentiate which string type it contains. Also the type is vchar_t. Just to have this written down. It should not require have a size/length variable. The stored string should be nevertheless null terminated, such that a cast operator to char or char such that would C compatible string. So you would always internally store the null byte as well, so that you can just return a pointer to the internal that should be const, just to be on the safe side, so that you can return a pointer to the internal data structure. So as you can probably already deduce, you can use the myInt as a rough guideline how to do it. Obviously this is a super simple case, it only supports multiples of int 32, So to properly implement it, there will be a lot of work needed, but at the same time, there should be no things that you have not yet encountered during this lecture, and this myInt should be a good demonstration of how all the needed casting mechanisms can be utilized. Generally, a good advice is to have at least a size, data, and type variable. You can, of course, want to go for a more complicated approach where you would have some internal object that which then stores the data and so on. So this can be made arbitrarily advanced if you like. Obviously, this is not yet everything. So the next task, but a option that doesn't need to be optional. Next part of this functionality will be let's see represent various data types. Okay. How do I remember this? So let's say like this. So this is let's have this PNC. This is like 1, 2 space, then implement for when so this is not very difficult. You just need to since you don't need to represent numbers bigger than 64-bit, you can just use the built-in operations, and you don't need to implement your own int with own addition and own subtraction for big int or anything like that. So this should be not too complicated. And then let's see what else would be good. Of course, we can add an optional optionally. So if you really want, you can implement for some extra points support for integers with more than 64-bit, which, as mentioned, is a bit more complicated, since it requires to handle the whole mathematical operations more or less manually, and take into account all the carry bits when you are adding and subtracting and so on. So this might be a bit more complicated, and since this is optional, you could opt for implementing not the full set of operators, for that only the most basic ones if you want. Okay. The last part is I hope it will not be too difficult. Alright, one more thing I forgot to add here, ABC, strings, and D, but this is more or less formality. Byte arrays. A byte array basically is just a char string, but it should have the ability to handle it as an own type, since for strings you have the expectation that they probably are null terminated, while for byte arrays you are expecting that this is some blob. Blob is a short for binary language object, just to have mentioned that. So here byte arrays which terminating null. So if you implement C, D is more or less trivial. You just slightly adapt the logic used for C, and voila. Okay, third point. The object contain provide functions. So it probably looks better if we shift this in. Oops, not this one. Get type, comma type should be an enum, the get size, data, binary size of data, c get data, const char ratio asterisk or const void asterisk, both are fine. If applicable, and this if applicable is that thing that will then a bit complicate the thing, because as I mentioned, such a variant can contain also also a list of variants. So this is so of course if you contain a list of variants, you would not want the ability to use this get data, because you wouldn't usually expect the data internally to still be like one large part. Let's say type size data. The other functions that you will need will be of course covered by this, all the constructors, destructors. I should probably write this to this just to be on the safe, to have this set. So have for each supported type as well as cast operators to that type. The object that will be like two. Comma optionally specific. So copy constructor, just to have this set, is this one. Is it this one? Oh, copy constructor, and this one is a assignment operator. Operators. Okay, so we want the assignment operator, copy constructor, and we want of course something to compare. So initiate compare function. Genau. We have the comparison operators. Okay, and the last part or let's maybe call it a final project part 1. Part I. Part 1, and separately we'll then have final project part 2. And here what we will want will be the ability for our variant to hold a list of or an array, and in the array that should be is enough of other variants. So add the type variant array, add and of So you would want to have a operator which gives you a C-variant reference and takes an int index. Actually, this is defined like this, as well as a get and a set function. The get function can be used for this if you make it return a value by reference, although it would be more convenient if you would implement them separately, such that this one really returns you a reference, while this one would be a const type function, so that it only returns you a copy. Obtaining a copy would be computationally more complicated, but at the same time obtaining a copy would give you the ability to, if you provide an invalid index, to just get a empty type back. One more thing that should also be added here. E maybe how do I say? We want a type which means that the variant has no type, that it's invalid, that it's empty. So and for a for an slash empty type, let's call it a variant invalid. Okay, so the invalid type will be what your variant starts its existence as when it does not have any values to it assigned yet. And this is quite good to know explicitly that you need that, because if you would implement it such that you would always require the constructor to get some other type from which the variant is created, you would not be able to create a variant which is, well, invalid, as needed to return from this get function here. The square bracket operator, I think we have demonstrated this in the classes. Was it is open variants? It should be somewhere. Here it is. Let's see if this would. I think I demonstrated it. Oh no. Somewhere I should have done. It should be. Or the search is not. Possibly also the search is not really working properly. But I think I have used that. Let's see what operators we have demonstrated here. No, just plus minus. Okay, so let's just add this here. Somewhere at the variant. So int and with this operator and we want this as reference so that we can, and normally what you would also could do is implement both, one as reference and one as const, such that you can handle both cases. So the const one returns a copy, hence if an invalid pointer is presented it can return successfully. So let's first do this one. If index is greater or equal count, then turn null, else return data from index. And this case, while here it can do this, it cannot return 0 because it needs a reference. So what we can do is we can throw an exception. Although in this case we cannot check whether we are allowed to throw it, because we always have to throw it. So our mechanism here will not be universal enough, and this is not an overflow error but a out of bounds error. or you could also call it an invalid index error. That both are fine. Of course, the other approach, what you could do here, actually we should implement it just as a demonstration. So we actually take our variable, and if this happens, we have two cases. One, this is set, in which case we just throw and are happy, and the other case is we just resize to index +1, and then we can successfully return the pointer because now we have enough data in our data variable. So this is actually quite a elegant demonstration. So that looks better, maybe like this. Yeah. Good. So you can use such an approach in your variant as well. If you make it hold a some data, then you can this way make it always return something if you don't want a crash, and then it also allows you to easily and conveniently resize your object. In principle, it would be convenient to have here a separate variable because you might want to throw in errors, but at the same time you might want to be able to resize this. Although in this case, probably the proper approach would be to call resize first, and this will bring us to a slight complication, because if you have complex data types, you cannot use realloc on it. You need to properly shift them around. So we will probably implement something during the next lecture, maybe later today, depending on how our timing is, that will demonstrate how such mechanisms could be done. But for now, let's return here. So we have here the ability, and then we will add a optional assignment to this as well. For array map of ASCII strings ASCII. So the optional assignment will be that it would be nice if you would implement also map support, which is quite easy. So once you have the array thing, the map is let's say a well, it depends of course how you implement it. It might be, there are more complicated ways to implement this as well, but the simplest way would be that you just maintain a list of the key of the name. So instead of storing a variant, you would store a pair of data, a variant and a key, and then you would just search the whole list. This would be very inefficient, but it would work. And of course, if you would want to use some sort of production map, then it would be recommended to use some either a binary tree or a hash table, such that you have very fast and lookup and insertion times. So having a list and then searching the list is extremely slow, especially if you need to do it often. It is not recommended practice, but for the sake of implementing something as a demo, it might be good enough. Okay, so I think this is it. Are there any questions? Is it clear enough? Does it sound like it's doable, or does it sound like it's too complicated? Let me know your thoughts. Yeah, so okay, so since there are no concrete questions to the subject, I mean, we could simplify this a bit. We could simply say that you are allowed to use SDL containers as internally within your variant. that is actually quite a good idea. So let's add this. So let's say oops, implementation suggestion. Make C variant. C variant object type, which can which will be no type which derived C variant array class for the data type a C variant map class for the C variant map type. So the way you would do it is you have your object which contains your type variable, your size variable, your data variable. You can either reuse the data variable or you can add an additional complex type variable. I would recommend reusing the data variable. So the data variable should be of type void asterisk, so you can assign anything to it. Just keep in mind that if you delete void, it will not invoke the destructor. So if you so when you are destroying objects, then you need to check which type it is, and if the type was C variant object or something that is derived from C variant objects, so any of these complex types like the array or map, then you need to cast it to the right type and then call the destruction operator. Otherwise you will get a memory leak. And then once you have these objects, which you can then make your primary variant class work with, you can have these functions like this index operator. Although this would be of course nice if this would also work for strings. I will quickly add this here. Is that a good idea? Well, it's better than not. No, it's not a good idea. We don't want this to work for strings. That would complicate things too much. So if you use this operator, the get and set functions, or the analogous functions for the map use case. So maybe I should write this down here. You know how they should look. Operator. In this case, we just have a different argument. Const char asterisk key. And of course, it's important to note that we don't want to save the value like of the pointer as key, but we want to actually save the string. So we need to create an own copy of the string and not just assign key, since key will go out of scope usually very quickly. So capital K looks better. So if you're using those functions, your approach internally would be simply check if variant is of a compatible type. If not, then you can throw an exception. That's a good point. We should add here another point for throw exceptions on yes. And we can add an optionally to this. So to configure exceptions multiple libraries, so that you can either just specify like throw always, throw on unrecoverable, don't throw exceptions, throw exceptions on unrecoverable errors, or throw exceptions on all errors, for example. Okay. No. No exceptions on or always. Or you could also implement a bit mask, or for each arrow type, so that you can say throw exceptions on different memory rated errors, but don't throw exceptions on casting when there is data loss, but throw exceptions if there is a type mismatch, for example. So this adds another point here. The variants must be able to convert. This is kind of implicit in how this is described, but we should add this explicitly. I will reorder the numbering here. Maybe that's point 2. Ensure that the can cast egg number presentation or vice versa, so that if you have a variant of type number and then you would want to use a variant, use somewhere a string, then you can just still use this variant and it will internally generate you a string type variant. So to be on the safe side, we should specify a bit more, because some castings of course will not be possible. So you can, if you have a variant which contains a string and you want to use it as a number, this is trivial because you can always return a number, it fits in a register. If you want to return a string, since we don't have an explicit string class yet, you would need to change the entire variant to contain the string then, and then return this as a pointer, which would change the variant itself, which is not how casting works. Casting should not change the variable itself. So let's think how to word this. I think adding a explicit string class would complicate things here too much. So let's say comma for other cases like string a cast to string const so the idea is when you can make a cast directly with the casting operator, then you should do it. Where you cannot do the casting, then you should throw an exception. So if a cast is not possible, comma, and provide on implicit and provide a cast function of this type. So the idea here is that you can make the conversion and then you return a new variant, which then is of the right type. So if somewhere you want to really use it, you could have, like, say, v1 is equals 1, 2, 3, and then if we want int x equals, sorry, this way it works fine. Meister is equals this of course cannot work. This should throw an exception, but what then you can do is you can just write as star, and this gives you a variant back. But since the variant then is a string variant, then the casting operator to return the internal buffer will work, and then you will get here a pointer that points. That would not be good. That would not be good because you need the data to be cast somewhere, so you would need a separate variable. Like this, v1 is v2 is equals v1 string, and then you can do this. Where it would be helpful is if you have a function void nothing, char stern s, doesn't matter what it does. So again, this would not work, but this star would work. And the way the compiler here generates code is that when this returns you an object, so in this case this v2, kind of implicitly, the object will stay alive until the function did its call. So in this case, the result of the further going casting operator will remain valid inside something we can access as, and only once we leave something, the created temporary variable which was returned by this function will be destroyed. So this match to this, and of course very important, let's write it somewhere here. So do not just provide the variant and that's it, but write like a program which uses the variant and exercises its different functionalities. So like casting, storage of data, etc., etc. For parts of the assignment. Maybe I should put it somewhere else. Okay, let's move this here. Implement basic. Okay. Implement variables. Test cases for the functionality of all parts of the assignment. Then we have final project, part 1 and part 2. Okay. Good. So we have this, we have this. I think this should be not too complicated. And here another note. The complex types, array and map. Your can use STL containers. So this helps a lot, and we will see in a second why. Okay, so this is the assignment. I think I already asked about questions, so there is no point asking again. This file we don't need, these two files we have. So now, since we have some time left, but not as much as we would need probably for a proper string of our own, let's create a new project, and I will show you the different STL container types which there are available, so that you know what you can use to help yourself with this array and map situation. So let's create a new project. STL demo create. Okay. So one thing that obviously is part of the STL is this std cout, which allows you to write text to the console. So you have seen that, I think, since it's always created by default, and as you see it works. But the more interesting and useful parts of STL are the different container types. So there are quite a few. So let's list them. Here we have vector, which is in principle just an array. Although there is a type which is actually called an array in STL, but unlike the vector, this array has a fixed size, so it behaves more like a real array. But generally, you would prefer arrays to be resizable, so just always use vector. The next one will be a list, which is a doubly linked list, unlike the one which you have implemented in C based on the in C++ based on the C example I provided. So you can iterate through it. You can insert values at both ends. So it's basically just your box standard doubly linked list. And then you get the map, which I already mentioned, allows you to associate values with keys. And there is also a thing called a unordered map, which is a hash table. If we have enough time, let's see, I think we have 3 more lectures, right? We have 3 more lectures, so we probably will have enough time to try to implement our own hash table. If not, then we can do it during part 2 in the next semester. Generally, the difference of a hash table to a map or to a binary tree is that a hash table, as the name suggests, unordered map, does not impose any sorting. So if we are iterating through the object and just retrieving elements one by one, they will be in a certain order, and if you then resize the object, for example, by just inserting one more object, it can end up completely giving a completely different order of elements. So it's not predictable in the way. Of course, it's deterministic, but the algorithm behind it is not transparent and also not part of the specification. So it just does its internal thing, and the only thing that you can rely on is that if you provide a given key, you will get a value for that key, or the information that there is no value at that key. There is no mechanism to sort these keys internally. They are sorted. Well, they are sorted internally based on an internal algorithm, but this algorithm can work in ways which are not intuitive to a human operator. A normal map, in contrary, will use and require this less than operator to generate a order of all the elements, and you can in fact misuse a map to sort a list of strings. Just by inserting all the strings into the map as keys, they will automatically get sorted according to the less than operator for a string type. Which brings me to the next thing, container type. This is the string. And from string you have 2 types, string and vstring. Both are in the same include. One is the normal ASCII string of bytes, and the other one is a wide character string, so it supports Unicode. And generally, in pretty much every case, it is good to use the STL string when you can. There is no need to create your own string classes, since you can use this std string in pretty much any project, and it takes care of all the string handling. So the string can be resized arbitrarily, so you can just append data to the string as you go. It is very convenient. It also provides search functions so that you can find portions of the string and alike. But let's now take a look how these are working. There is more, of course, that is part of the STL. It is not just containers, but initially it was mostly containers. All the other things got added later, and the containers here are really something that is also kind of platform independent. While the other added things like threads and synchronization for primitives like mutexes and the like, while are implemented such that your code will compile on any platform, internally they use completely different operating system specific mechanisms. The typical containers which we see here, in contrast, always do the same thing, because they only need memory allocation and the standard C++ functionality. Okay, so let's start with the vector. So std vector, vector, and then since as the name suggests, standard template library, here those container types are all implemented as templates. So it expects some arguments, In this case, as you see, we can either specify just a type, or we can specify a type and an allocator. An allocator would be something that helps us to implement some own memory allocation, but this is usually not used, so we will not utilize this functionality during this lecture. We will only specify a type, so let's say we want int, and then of course we provide a name, int vector, and it starts out as a vector without any size, but if we know how many elements we want to add, let's say we want to add 10 elements, we can reserve 10. And reserve is different from resize in as far that reserve will really reserve this memory but will not assign any value to it. Resize will reserve memory and assign 0. And the important thing is that if you use the size here to get size, here at this point, it would give you out 0. While after resize, it would give you 10. So if you want to assign objects and assign data, and you don't need empty data anywhere, then this reserve is a better approach. Then we just use pushback, and we can add some value. So let's say for we just add 0 till 9 here, and then what we can do is we can add say 10 and 11 and 12, and this will still work. So pushback will always succeed, and it will just, if it doesn't have enough memory, it will just then allocate a new memory for the operation on the fly. So this line helps with performance, but is not necessary for reliability. And we of course can also use push font. Can't we? Okay, insert. We can insert at the font. Punkt. Begin, comma, -1. Okay, let's run it. And the IntelliSense in Visual Studio allows us quite easily to look inside. Of course, such a insert operation will be more computationally intensive because it will need to shift everything inside. The nice thing about such a vector is that the data it contains are memory aligned, so we can just get a int asterisk int data, and then we could have a loop for int e is equals 0, and e is less than vector. We can use size so that we know how much is there, and then I++, and here let's say we want to print all the numbers, so we'll use here our thing. We can shift some zeros into it and run the code, and it will write. We don't want to write the memory address, we want to write the values. Suck. You see, it works fine. And there is an important thing to keep in mind, that whenever we change vector, the data inside gets invalidated. So if we would now push back another 10 elements, very likely initial data might get corrupted. It might not, it might use resize and we might be lucky, but well, actually it worked out well. But there is no guarantee, so in principle at some point the internal pointer may get a different offset. So if we are referring to data, we should always then use it and not do anything with the vector, not insert or remove elements, etc., because doing so might invalidate the whole pointer. Usually, I guess removing elements will not be that critical, because it will just in place shift the array. It will not probably shrink it instantly. But of course, if we have removed enough elements at some point, it would decide that it could shrink it to save memory, and then it would invalidate the pointer. So given that this is a bit of a risky way of doing things, the next way we can use is, let's say, here \n, is we can just use the square bracket operator on our vector directly, and it will also give us its content. And this operation is safe because it will, if the vector would to change internally, it would then of course always still access the right memory. The only change that it is not safe against is if we would shrink the vector, and our condition here would not depend on the size. So if we, for example, cache the value, which kind of looks like a performance improvement, but if we would do this, then if we then reduce the vector in size, then the result could simply be that the vector will that will try to access invalid address. We can simulate this by doing as if there would be one additional entry, and as you see, it throws an exception, which is here presented as an assertion, and if we ignore it, then it crashes a few lines later, since it cannot return a value from a non-existing offset. There is yet another way how we can go through this data structure. We can use so-called iterators. I think I mentioned iterators already when we have been looking on our simple list C port, but here now we will see how this actually works. So for we'll use the auto keyword to not have to type out the whole iterator. We call it e is equals vector punct begin, comma e is not punct end, e plus plus, capital E. We should use plus plus e. In principle both work, but this one is the one that is recommended to be used if you want best performance. And then what we will need to do is we need to use the asterisk operator, which is simply a custom operator on this iterator object. As you see here, when we go on auto with our mouse, it shows us how this object would look. So it will be an std vector brackets in double point iterator. And now if we run it, we will of course still get the same values. And while this might look like I forgot the new line. And while this might look like a bit of a cumbersome way to use it, since this is much more convenient, this mechanism is necessary when operating with any sort of data which is not with any sort of container which is not memory aligned. So if we have, for example, our list, which we can try. So let's not copy anything. So let's do it by hand. Std list, again int list, and here we will push back 0, or actually we can be a bit lazy and use our loop here, 0 till I, punct. As you see here, the list actually also contains this push front command. On vector you can use insert to get the same result, but on list you have push front. What you not have is the ability to access elements by index. So int list doesn't have a square bracket operator. And here, if you want to iterate through everything, and it also doesn't have like a data either. So the only way how you can go through this list is to use this iterator mechanism. And as you might remember, in our own list we had this special function which allowed us to iterate by calling a callback function for every element. This approach here is more elegant, and if we will have enough time, we could improve our list with this mechanism maybe. So as you see here, it also allows us to go through everything, but only these iterators work for lists. Okay, we have our list. With this list, in principle, you can still use insert, but you wouldn't really know where to insert. So what we can do is we can take auto list iterator begin. Then we can have a loop for let's say kleiner 4 e++, then l plus l. So basically what we are doing is each time we call ++, we are shifting our iterator to the next object, and then it has a reference to the object which then is somewhere inside the list. So we can start at the end of the list and then move our way all the way to whichever offset we want. We could use such a mechanism with our simple list as well, since we can always go from one element to the next and next and next, or in the double linked case also back. We just start at one end and then iterate through it. Obviously this is very inefficient, but it works. So let's run it. And as you see, we have inserted 1, 2, 3 at the 4th position into our list. And of course we can do this also to remove elements, so we could go a bit further, but not so much. Let's go just 2 elements, and then we use erase. Also erase works here with vector as well. Erase, and as you see, you can either specify a range, so you can specify like 2 iterators and everything between them will be erased, or you can specify just 1 iterator. And here, if we want to delete more elements, we could actually use this demonstrator one. We could erase this one, and then we can reset our LE to begin. Then make a auto LE2 is equals plus LE, then we plus LE2, and then we erase everything from LE to LE2. And just to be on the safe right, so the -1 entry will stay because here we advance it by 1, so we should delete 0 and 1 from our list. We have a minor typo, and as said, we have removed 0 and 1, 2 stays, 1, 2, 3 we have inserted, and the rest remains unchanged. So this is the list, and the last major commonly used type will be the map, and well, or rather D maps, since we have a few maps to talk about. So the simplest case, of course, is std map. Then we provide a key. Let's say, well, let's go with an integer, and then we have to provide a value. So let's go with using our string here. So std string. We could of course use a string as key as well, and the wildcard version will be just vstring. But for now, let's just go with the normal string. Map, my map, and for my map you can either use insert, but the insert works a bit weird. You could insert with iterators, but what you also can do is std make pair key, let's say 1, and let's just write out 1 and 2 and 3 and so on, and 2 and 3. Okay, so this one way, and the other way is we can use the square bracket operator. Sorry, 4 is the next one. And as you see here, automatically from the C string, the compiler sees that there is a constructor for std string that takes a const char asterisk as argument, and then it creates a string here, which then is assigned to the reference, which is returned by our map. And what we also can do is we can override values, so we can again go to 4 and let's just make this, replace it with all 4s. And then of course, if you want to go through it, if you want to just retrieve values, we can use the square bracket operator. Let's say std string num is equals map small s map 3. But this doesn't give us a way to like go through all of them. We would need to have like a list of all the keys to then use the square bracket operator. So what we can do, of course, instead is we can again use our iterator approach, just that with the my map. And the iterator here works slightly differently. Instead of asterisk iterator, use iterator arrow operator, and then use first one is the key, and the second one is the value. So this thing is equals second. If we run it, we will see that it works. We should add commas or something. This doesn't look nice. But in principle, I forgot that. Let's make it pretty before we take a look on what we've done. So this one was missing here, and also it was missing there. And let's change this everywhere to comma space. I think that's one. Okay, zack, and voila, 1, 2, 3, 4, 5. And this map is very fast when operating. So if you double the size of your map, so if you are inserting elements, and let's say you have inserted 50 elements, and then you keep inserting elements, and then you add 100 elements, and then you want to insert the 100th first element. The complexity of the operation to insert the 101st element in comparison to the complexity when inserting the 51st element just rises by one operation. And like saying operation is like an abstract term, in this case it means generally a comparison operation within the internal data structure. So the time needed to insert an element doesn't grow linearly with the size of elements in your list, but it grows rather like just a logarithm of the amount of elements that you have in your data structure stored, which is a very favorable time behavior. There is another type of structure which has an even better behavior, which is this unsorted map or hash table. There the insertion time is constant. So if the map, if the table is not somehow broken by a inappropriate choice of the hashing algorithm, then ideally every insert operation will take the same amount of time, no matter whether you have one element or a million elements. There is some practical overhead that might be encountered there, since at some point the size of the hash table internally will need to be grown. So sometimes the insertion operation will take longer because the table needs to grow. But this should not be something that is like done every time you're inserting an element. It should be large enough from the get-go, and if the hash function works correctly, you should always get at most one element per table entry, which will give you a perfect timing also when retrieving elements by key. Yes? Um, in principle, the pair is a template, so if you have an old enough version of your compiler, then it will not work. But if you have a newer compiler, I mean, this one is set by default to 2013. Okay, we cannot even set it to anything older. Generally, all the newer C++ compilers are smart enough in such a scenario to find out which arguments are necessary. But if you want to be compatible with like C 80 is too old, 98, then you would probably need to write it like this. Documents. With anything that's somewhat reasonably modern, it is smart enough to figure this part out on its own. I will just put this as a comment. Okay. It is. Okay, so now let's continue to the next one, which pretty much behaves almost exactly the same. It just uses a different mechanism under the hood. Unordered map, why my umap? Or my table, accurate table. They should have called it a table, not unordered map. That is just not nice. Oops, too much. Okay. So as you see, it kind of works the exact same way, given the interface, just that internally it uses a different mechanism. The map, as such, is a binary tree, which is balanced, and if you are searching in it, you can, with every comparison operation, eliminate half of the amount of the elements which are remaining. So if you have, let's say, 8 elements, then you will need 3 comparisons to find the right entry. If you have 16 elements, you will only need 4 comparisons, and so on. So it scales very favorably, but it is not instantaneous, and when using something that can easily be hashed, so where you can quickly generate some numerical representation of it, then such an unordered map is even faster. So we could of course try to run like a benchmark to compare which of those really works faster, but I think this is not really necessary. So if you are doing something time critical, just do your own comparison, your own benchmarks. This is always a better approach than relying on someone else. And there is one more aspect to this map that we still probably should mention. That is the multi-map. So std multi-map, and a multi-map pretty much works the same way like a normal map, just that you can have multiple entries at the same key. So my mmap, and I think the square bracket operators might not work. Okay, so as you see, yeah, they don't, simply because the semantic of such an operator assumes a unique association, so that one key has one value, and then if you provide the key, you can change the value. But since a multi-map can have multiple entries, you cannot use it. Which of course brings us to the next point: how do we retrieve a single value? All the different map implementations provide a find function. Auto f is like find, and then we provide the key, and it will give us an iterator, or it would give us the end. So if this is equals end, then there is nothing, so we should check whether it's not alright, and we have used num, so this will complain. And this is num1, no, this is num2, this is num3, the first one was num1. So we check whether this is not end, and if it is not end, then we can say num is equals second. And the important thing is here that in this case this will return only one of the entries, so we can actually insert here multiple entries, so 3 and 3 and 3, and now here we will just get one of them. I think the last one, if I recall correctly, but I might be wrong. Right, and this goes away. Suck. And we got the first one. Okay, then it's the first one. It is specified somewhere, but I didn't remember which one is the specification. And as you see, right, we did not do something. Right, we didn't do those insertions. So it's coincidentally the same length as the other one, but of course it contains 3 3s instead of 4 and 5, since we have not inserted 4 and 5 into it. And there are more. So first of all, if you get an iterator, you can obviously go to the next one. So you can have your num2 a comma b comma c. So in principle we could num a is f plus plus. So this way we'll get all the frees. Oops. Just that if we go too far, I mean we should add some 4 and 5 to this as well. 4 and 5. 4 and 5. So if we go too far, let's just go too far on purpose here. We'll just skip one. Then we will just get the 4. So it just gives us the iterator, and we can use the iterator to continue, but it does not tell us how many entries there are. So in such a scenario, let's say we would want maybe remove all the 3s from our list, from our map. So in this case, if we would want to remove all of them, one thing I forgot to say, we have here 3. The map also has an erase command, but unlike the other ones, it doesn't only take iterators, but it also takes values. So we can erase 3, and it will just do it. So we just provide the key, and we don't need to do anything else. Of course, what we can do, if we have here our find, we can also erase that. So map punct erase f, and this will work the same way, just that it's a bit more complicated, and we should of course also check whether there actually was something to erase. And what we also could then do is, of course, we could make a copy, f2, let's call it f2, which starts out as f. Then we can make a loop for f2 is not equals to end, because it might be. And then here right, so we generate the next f3, which is for now just a copy. Then we advance it by 1, f3 plus plus, sorry, plus plus f3. So this one is now the next level. Now we check if this thing is end. Actually, if this thing is end, then we can break here, so we don't even need a condition in our loop. We can make an infinite loop. But what we will want to do is we will want to advance f2 to be f3, so that we delete everything until the end. But if it's not end, then we can check if f3 first is not equals 3, then we break. This way we will end up with of the iterators f until f2 containing the range of all our threes, and then it will just remove the threes from our list. This is one approach. The other approach could be, of course, to erase inside the loop. So erase, the way it works, if you provided an iterator, will return you the iterator to the next element after the element which you have just removed. So if you want to clear the list entirely, like remove everything, you can have let's start with this. But here you just have I is equals my mmap erase e, and of course we could, this way you can clean the whole list, or we could have here find let's say 4. Then we have here the comparison whether it's AND, and if it's not AND, so it is not AND, and e second, no sorry, first, oops, is equals 4. So in this case this thing will, let's add a few more 4s as well. 4, 1, 2, 3. So this way it will also erase all the instances of 4, and it will break out of the loop as soon as the next, I forgot the plus plus, I didn't, I have it here, like this x like the plus plus. So it will advance as long as, until it finds either the end or the next element does not belong to the value range. So as you see here we have 1 3 for some reason we inserted. Alright, it's the wrong one. Wait, 1 2 3. This one was for the hash table. This one should contain those things. Somehow we are missing one printout. So we have here our normal map. Then here we have our multi-map. Let's put the breakpoint here so that our one now should be the last one. Now we have a deadlock, that's the problem. We have somewhere our infinite loop never terminates, so this thing advances. Okay, so we start with f being f2, f3 gets advanced. If this is end, then it will break out, or if f3 first is not 3, and then it should break, but it doesn't. Right, because we forgot something. If it is, we need to advance this further. f3 is f2. Okay. So what happened was our program just ran forever. So it should be this printout. So we have eliminated the 4s, but 1 3 is still there. Why is it there? Did we reinsert it, or did we do something else wrong? So we start with num. The last one is here. Okay, so the logic here is still not fine. So if this is not true, we always want to advance it, because the previous one, let's see, so we take this, we advance this, then we compare this, and this is what this one needs to point one further down, then it will be fine. So basically we can just we don't need the f3, we don't need the f3, just plus plus f2, and that's it. Let's make it a bit more pretty. Okay, and here we can have an either or, in which case we break through this. We could actually also just put, let's do it here. Okay, now we should remove, yeah, now it worked fine. We have removed the 3s and the 4s using 2 different methods. So as you see, these containers are quite useful, because generally you want to do something and store data. If you used Python in the past, you know that without arrays or dictionaries that would not be fun to use, and this library basically gives you all the things that you need, as well as this already used here string, which removes from us all the burdens of using a null terminated string of a fixed length. So my string. Let's see what we can do funny with our string. Well, many things. Obviously we can assign something to it, let's say 1, 2, 3. But the nice thing is that we can just use the plus equals operator to 4, 5, 6 to append things. Or we can use the append function. 6, 7, 8, 9. And it contains a pushback command which can take a single character, so we can also push back 0, and then we can search in it, find, let's say, a 7. Process equals 7. We can, of course, if we found the position, we can create a new string, std string, my substring, which is also very useful. We can extract any portion we want. So let's say we use the substring function. We provide an offset and a length. Let's say we want 4 characters. Forgot the substring function. We could, if we want, then erase using the same semantics, position and length. And now, basically, what we did is we have extracted a portion of the string. So our we broke something. Doesn't like one of our offsets. Which one? Position. Oh, position. It didn't find. Oh, sure. It didn't find 7 because that needs to be in brackets. And as you have seen, the find returns you -1 if it doesn't find it. So in this case, we had our string from which we now removed everything starting at 7 until 0, and our my substring now contains this 0 things here. You can of course change the offset to 3. Then we will leave the 0 behind. So as you see, it allows us for any amount of very convenient string manipulations, as you might be used to from Python or JavaScript or other languages which provide you a complex string class. Just that in those other languages, the string is kind of an integral part of the language, while here the string, while being integral part of the standard library, is completely implemented as within this language. So on Python, at some point Python itself is written in C++, then your string would just be some C++ object within Python which is doing things, while here in C++ obviously the string is just implemented directly. So this gives us in principle a large flexibility, because we could implement our own string and it would be in no way less performant than the not quite built-in std string. While on other platforms like Python or C# or JavaScript, in principle you could create your very own string class, but that would never be as performant as using the built-in string, which there is just a binding on some internal native object. Right, so what could we else do? I have 13 minutes left. Well, we could run some benchmark just for funsies. But maybe there is one more thing that I can show you. As you have noticed, of course, here we already used a std type as an argument for our map, or anywhere else, but in principle you can use the square bracket operator. Let's say let's put this one. To call a function on the object which is held by our map, so like this. And to demonstrate this a bit more explicitly, we can create a std map. Key will be int, comma std. Let's use list. of type std string. So as you see, we can my list map list. It's a map of lists, so map list. My var. I'm too lazy to come up with a good name. Now we can, as mentioned, let's see, one punct pushback one and so on. So as you see, you can use these objects with in principle any class. So we could also just create a map which would contain our myInt, for example, as the key. There is only one requirement, that whatever is used as a key must offer a less than operator. If it doesn't, then you cannot use it. But you can, in principle, always define a custom less than operator whenever you want. So we could try this out. So let's say struct as my key. It will contain int v1 equals null and v2. So we want to use this as a key. Then we will want to give this thing a constructor int v1. v1 is equals file. Let's go file1. Oops. File1, file2, and though it might be that it will create a for us, but I think it will fail. Yeah. The IntelliSense is not smart enough to complain, but the compiler as such tells us that it's missing the less than operator. And if we have our own class, then of course we just create your less than operator inside here. But in principle, you can also write a full operator. Then you have these const reference L, comma R. So an operator does not need to be inside your object, not always. But, it needs to be outside of the function. So let's put it somewhere up here. What is this completely about? Operator. Yes, we need to choose the operator actually. And this needs to have a different name. And now let's say if L punct val1 is less than v2 r val1, then return true. So if this is given, then it's true. If this is not given, then we check the second variable. And if this is also not given, then it's false. That is all we need. For example, a use case here where you might want to create your own object to store and use this object as a key would be if you would want to use an IPv6 address as key, and obviously if you would be implementing something that does any sort of network communication, you might want to be able to find your clients based on the IP address, especially if you're using UDP, where you don't have explicit connections, but just data communication based on port numbers and IP addresses. So in such scenarios, it would be very useful if you can quickly find your clients based on the IP from which a packet came. And since an IPv6 is 128-bit large, you cannot store it in a built-in type that would be compatible with map. So you would need to create some sort of MyKey. So for example, in this case, it would be, if this would be an IP address, it would be a byte. Include everything with a byte. We did not. Okay, answer in char 16. So it will be then at val 0 for IU test case, and this would of course need to be changed For int less than 16 e plus plus, and then we just go val from e, and we have a class that what I forgot. Okay, I cannot initialize it this way. I can initialize it that way, and val from 0 should actually work. Why doesn't it? Const char next image should be of course a char, and unsend char, but that should not be the reason I doesn't want to. Damn it, I used the valve already. First. Okay. Now of course we are missing some mechanism to set the whole thing properly, so we could for this it's good enough for the use case now. And as you see, you can easily create your own key, but now let's just run it. Alright, and we want to print it as well. Zack. Of course here printing is difficult, but you can use value 0. And second is a list. We cannot print a list. We can use front to access the first element in the list. Oh, and by the way, there is like an analogous functions to push front back. There is a pop front back which will remove one element from the front or from the back. So if you need any sort of queue, then you can just use such a SCD list and just push front, pop back, or vice versa, and have a queue which has a first in, first out behavior. So let's run it. And as we see, it's working fine. Well, actually it's not. So we have inserted those elements. This is okay, we have overwritten them because this is not a multi-map, so let's go with multi-map. But also value from 0 didn't work because this thing doesn't take this as int. Let's cast this to an integer. Because it was a char, then it alright, we cannot first of all that's called multi-map, not nmap, but the second problem would be that we would need to use here insert. So let's just no, that actually it should work. Since we're accessing the same element, but we're accessing the next entry, so maybe we should make the this demo proper. So we have this until here, and now we need to change this path to access our list inside. So use a different letter, let's say J, from I second. It's complaining about something. J plus J. It's complaining because we are missing here the semicolon. Okay, so we have J. Actually, we don't need the brackets. This ones, and now we just will push out J asterisk, and then I don't know, some character, a vertical bar to delimit the entries. And this will work because the first time an element gets created, the next time we are accessing the existing element, and then we're just calling the pushback function. So that should be fine. And zack, as you see, the data are there. So also we are running out of time, so I think it's a good moment to stop for today. The next week is a holiday, so we will see each other in 2 weeks from now. I think you will have enough to do with the final project, so there will be no homework today. If you have any questions, you can email me at any time. Yeah, and that's that. I would, since you now have a holiday at your disposal, I would strongly suggest to use this time to work on your final project. since at the end of the semester you will have obviously other exams and tests and so on. So it would be a good timing optimization if you do the things that you can do early, and then you have all the time at the end for those things that cannot be done before or later. So, but this is just my advice, so it's up to you how you manage your time. During one of the next lectures, there are a few things I would like to show you. One is, of course, more of the STL, so like the smart pointers which are built in. So I think this will be the major subject during the next lecture. We might, if we have enough time during the next lecture, use some time to also implement either an own array class, which would probably be quite useful if you need some inspiration for the second part of the final project, or we could implement an own string class, which is kind of similar to an array. It just adds all these additional functions which are string specific. And one thing that I want to show you, but probably we will do this on the very last lecture, is how you can interact with C++ if your own project is only written in C. So there are ways how you can, in principle, by hand implement all the mechanics that C++ offers you. It's just very cumbersome, but it is doable, and it, I think, is quite a nice thing to have seen at least once, so that it gives you an additional insight into how C++ really works under the hood, and that it's really still extremely a low-level language. It's very close to what the hardware is doing, so it's really not in no way comparable with other languages like C# or Python, where you more or less are confined to what the language allows you and cannot in any reasonable way break out and directly access the hardware. Okay, so since the time is over, I think this is a good point to stop talking. We'll see each other in 2 weeks, as I already mentioned. Have a nice weekend and a nice holiday. Bye bye.